Today's webinar is really very important in the sense that this addresses the solution for managing plastic waste and the issue which the whole world is facing by generating a solid waste which comprises over 70% weight percent of the plastic. So we have our speaker, Dr. Suryasarathi Bose. He's a professor in the Department of Materials Engineering, Indian Institute of Science, Bangalore. And prior to joining IISc Bangalore, he was as a faculty member. He joined IISc in 2011, and he was a postdoctoral fellow in the University of Leuven, where he was hosted by Professor Paula, and he received his PhD degree in materials engineering from IIT Bombay. So Dr. Bose's research interest includes recycling and upcycling of plastic, and the Vitrimer membrane for water remediation and desalination, hybrid nanostructures, material for heavy metal adsorption, structural property, correlation in polymer blends and nanocomposites, concentration, fluctuation, and segmental dynamics in multi-phase systems, directed self-assembly using demixing in polymer blends as a tool, and the materials. He also develops the material for EMI shielding and microwave adsorption. So Professor Bose published more than 250 articles in international journals, and he's recipient of many, many awards. So a few of them, which I'm mentioning here, is a prestigious Swर्ण Jayanti Fellowship from the Department of Science and Technology. And he also received the NASI Scopus Young Scientist Award, Professor Satish Dhawan Young Engineer State Award, and he's also recognized by different national bodies here. And he is also the Young Associate of INA, and also is a member of Indian National Young Academy of Sciences. And also he's a member of National Academy of Sciences, India, NASI. And he also serves in a lot of editorial boards of international journals. So this talk will be moderated by Dr. Susila Venkatraman. So she's a development professional, and she is also a chair of Arogya World India Trust. She is also on the board of two NGOs, namely SGBS Unnati Foundation and also the IITACB here in Bangalore. And she is a partner with the NUT Center for Social Innovation. So Dr. Venkatraman was the principal director of the Asian Development Bank's Office of Information System and Technology. She was there till 2015, and she was responsible for planning, implementing, and maintaining ADB's communication and information technology platforms and the system, as well as advising the ICT for the development. So she has done her PhD from Birla Institute of Technology and Science, and a master's in business administration from Faculty of Management Studies and from University of Delhi, and again a master's degree in physics from IIT. So for audience, please post your question and answer in Q&A box, and that will be taken up during the discussion and during the break, during the talk. So now over to Professor Bose.
Thank you, Abba. Let me share my screen. So let me thank the organizers once again for giving me this opportunity. This is a wonderful opportunity where I can showcase a little background of how plastic waste can be managed using newer solutions that I'm going to talk about, and what we have been doing in IISc towards this particular cause. So before that, my name is Surjo, and I'm a faculty in the Department of Materials Engineering. I'm also heading the polymer processing group here and a center of excellence in plastic recycling and upcycling. And this is from the joint effort from Manjushri Technopack Limited. And the goal here is to find sustainable solutions for effective recycling. So let me register one date in your calendar, which is 28th of July, 2023. And this is called the first plastic overshoot day, which means the amount of plastic generated on that particular day exceeds the actual management capacity. So this is something that we don't want to register, but I would like to register because it also tells us that we need to really work on this solution and get a immediate solution for this growing problem. So to take you a little bit on the statistics published according to Plastics Europe and CAC India reports, I'll pull my laser pointer here. So from 2018 till 2022, as you can see that the plastic production has been growing, and right now it stands more than 400.3 million tons, and of which the gray bars that you see here is fossil based. There is little bit effort on recycling mechanically and a very small effort on recycling chemically the plastics that is produced. And what you see on the screen are cumulative numbers. And as we stand here in 2024, these numbers might have grown up by now. So which also means that our dependence on plastic is increasing, and the solutions that we need to find out, which should be at war footing, is not happening. And that's the reason why the first plastic overshoot was just around the corner. And I'm sure it'll be very tough for us to go back and say that, okay, we have either recycled and put in use of the plastic that we have already produced, and we have a planet that is free of plastic garbage. Before I get there, there are two things that one needs to keep in mind. One is called post-industrial recycling, and the other is called post-consumer recycling. So post-industrial recycling comprises of plastic scrap and waste generated during its production or any component at industrial scale. And post-consumer recycling means that once the product is out in the market and the consumers have used it, and then they discard it. If they have discarded it effectively in a proper bin, they would have been recycled, but that's not what is being practiced. And that's the reason why we have plastic littered all across the globe. So PIR, post-industrial recycling, is relatively cleaner feed because it is uncontaminated, whereas post-consumer recycling, because it is not properly disposed of, is often contaminated. So it is much easier to recycle post-industrial recyclate rather than post-consumer recyclate. But since our dependency on plastic is growing up, we really need to find solutions for effectively recycling PCR, which is post-consumer recycling material. And the statistics that you see here on the slide, Asia contributes about 50% of the plastic production, and India alone, stands very high. And of this, 43% is a short use polymers. I didn't use the term single use because that has no meaning, because we tend to use them for relatively shorter period before we actually discard. So I keep telling that we need to retire them at the right time if you really want to give them a new life. So therefore, we have a crisis at hand, right? This is one of the famous image from the Everest base camp. Every season, we have tons of plastic garbage right there. And of course, since we did not dispose them off, they are everywhere in the water bodies, landfills, and so on. So this is the crisis at hand. This could be sorted out by organized disposal. So currently, we don't dispose them off in a proper way, and that's the reason why plastics are everywhere. So I keep saying that don't ban me, but manage me better. So banning is not a solution. I'll show you in a while why is it so. And also, if you try to retire them at the right time, they can be given a rebirth. But since we don't do it, and that's the reason why I'll show you in my presentation that why can't we just recycle them as is, and why there is a need to look for solutions in chemistry. So certainly the current practices are not enough. Although US, the per capita consumption is quite high, the percentage that is recycled is not that great. Although India, which is relatively doing better in terms of recycling, but still we are not that far. So recycling efforts are not enough to solve plastic waste problems, and we need to find advanced recycling or emerging solutions. And that is the scope of my talk today, where I'll show you some of the emerging solutions that are coming up in this field. So this is the plastic footprint by humans. The global average consumption of plastic is about 20.3 kgs per person. An average Indians consume about 5.3 kg per person. And this is a whole list of countries that produced plastic waste. And no country wanted to top here, but of course we have topped there in number 3, where our consumption, since it's quite high, although it's not close to the global average, but the waste that we generate is enormous. So this is kilotons per year. So if I take a look at the 3 major FMCGs companies, Hindustan, Unilever, ITC, and Dabur, and I have some statistics which has been published in these reports that you see on the slide below there. These are the plastic put out in the market in tons. And as you can see, that the amount of plastic that most of these FMCG companies put in the market is huge. And these numbers would grow up because there are no alternative to this wonderful material. So I keep referring to this as wonderful material, although the whole world keeps cursing it. Since they are seeing it littered everywhere, probably that's the reason why they're cursing it. But actually, it's a wonderful material, and we need to find solutions how to manage them rather than keep cursing it. So although the per capita consumption of plastic is less, the waste generated in this country skyrockets. And as you can see in the statistics that we produce, or we rather waste, we don't manage them well. And that's the reason why it's littered everywhere. So I come back to my first slide where I showed you this number. I only have the data from 2022. And if you see this 400.3 million tons of plastic that is produced, if I have to do an anatomy of it, I could see that most of the plastic is dominated by PP, which is polypropylene, polyethylene, PVC, and the other polyethylenes. And of course, there are other plastics, as you can see on the slide. But since the market is dominated by these olefins, which are again wonderful material because they offer uniqueness in terms of packaging, production, producing, processing, etc. So that's the reason why they're everywhere. And of course, the economics keeps them live younger. So if you look at here, the multi-layered packaging, I'm sure many of you love chips. And you must have also heard that the chips packets are impossible to recycle because they contain more than one plastics. And therefore, they're called multi-layered plastics, which is true and false at the same time because there are ways to recycle these chips packet. And we'll see as we move along that how different startups are actually trying to recycle them. PET, most of us have seen them in water bottles. LDP, HDP, polypropylene, which we commonly refer to as polyolefins, are almost everywhere. So I just brought few items or objects that you can see on the slide. These are the products that are made out of these plastics. So the polyolefin demand in India, as you can see, now we are in this year 2023-24, and you can see that the amount in tons for the polyolefin put together is enormous. And PP, of course, polypropylene dominates this. And this is the production capacity in kilotons. This is from our own country. And the reports are drawn from CSE India reports. So this is where polyolefin stands. So since it is so versatile, it's being used almost in every product, every applications, both food and non-food. In food grades, especially in FMCG products, it can be as primary or secondary packaging, and in non-food, they can be used anywhere. So since we produce so much of polyolefin, given their versatility, we also need to know how do we effectively recycle them, since we have produced it so much, loved it, and we have used it in various products. We also need to effectively find solutions which can give them a rebirth. But that's not what is happening. So what happens to all the plastic waste, or what happens to all the plastic that was produced and used and then abused? So I have a couple of very interesting discoveries. So this is one of the tunnel boring machine from Namma Metro, Bangalore. And while it was digging, it got stuck in a muck, and they were not able to understand what happened. This is about 30 feet below the ground. And when the engineers went there to see what happened, they found a pile of garbage. So, which was once a landfill, now the civilization is nicely growing on the top, but 30 feet below is a landfill where all these plastics were dumped. And this was in the news because the work got halted for about a couple of weeks because all these boring blades, were stuck with plastic and rubber, so they couldn't be operated, and therefore the work got halted, and that's where it's in the newspapers. And of course, you see all these disturbing images of the fishing nets getting strangulated and all the plastic waste all over the place. Need not to mention about the Great Pacific Garbage Patch that you can see, which can also be seen from the space. So this is where all our plastic waste goes. Since we are not effectively recycling, or there is very little value to this plastic waste, and that's the reason why it is everywhere. So by the way, next to the plastic pollution is the textile waste, which is growing, and we would be discussing in one of these webinars very soon about what do we do with these used textiles that we have all filled up our wardrobes with. And most of it have polyesters, and each time you wash them in a washing machine, you generate tons of microplastics because they are made out of polyester. So all the microfibers from polyester goes into the nearby water bodies or end up into the ocean. So the Great Pacific Garbage Patch is what you can see, but the million tons of microfibers that you can't see are also lying down below it or floating all around. So this is where our plastic waste is heading to, and we certainly need to understand that how these plastic waste can actually be managed well. So the question here is, what do we do with the plastic waste, right? So India recycles, as I said, that we are doing relatively better than others. So we recycle about 12.3 of the plastic waste that is generated. Of course, 20% of them are often incinerated. And from the latest data that we see here, so India manages about 14.2 million tons of plastic waste. And that is about 71% of all primary plastics produced by the nation. Again, if I have to take a look at most of the FMCG companies, which are the largest consumers of plastic, so this is the number that comes out. The source of plastic is mostly fossil derived, and therefore they cannot degrade on their own. And therefore, if you are dumping them in the landfill, they're going to stay there forever. They also use very little recycled plastics, right, for packaging their products. But the numbers compared to these figures are extremely low. And that's the reason why we need to really find out ways how to use this recycled material back into the products and so on. So these are some of the statistics again for post-consumer recycled plastics that has been used or is being recycled in various countries. And as I said, that Asia is one of the largest producer of plastic. It also generates a lot of plastic waste, but how much of it is recycled is something which is worrisome. So the question here is, how do we recycle them? So we have two ways that you can do. One is called mechanical recycling, which means after the consumers have used it, you collect it, you sort it based on its color, you grind it, and then convert them into flakes. And these flakes can be again used to produce products. But it's not as simple as that, what you are seeing it on the screen. There's a lot of science behind how do we use these flakes back. And I'll show you in the later part of the talk that these flakes have already downgraded, right? Since polymers tend to lose their properties in every sequence of processing, they are not the same material that we started with. So therefore, it's very difficult to recycle them back to the same product unless you do some chemistry which actually upcycles them and brings back to the same state where we started. The second option we have in our hand is chemical recycling, which Reliance and others have been following up. So you have plastics, then you have plastic waste, whether we can depolymerize or strip it down to monomers from where we made the polymers and try to repolymerize and make the polymer back. However, all the statistics that I showed till now, the chemical recycling numbers are very, very small, which also means that this is not being adopted widely. And we should bring in regulations where both mechanical and chemical recycling is effectively followed. Chemical recycling often is also made into value-added chemicals, and therefore the energy solutions come out here with recycled plastics. Since it's not being done effectively, we don't see much from the statistics. So let me bring you to this pie chart here. So this is the total plastic waste that is recycled. It's a small number. 19.8% is burned, and the rest is unaccountable, which is now, you saw on the slides, where does all this go? So in future, what we should, all of us, try to do is to increase this number significantly so that all the plastic that is produced actually is being either recycled, or should we turn our focus to biodegradable plastics or biocompostable plastics so that they disappear in the environment on their own and we need not worry about recycling them. So before we get there, I have few paper clips which shows that India joined other nations in banning single-use plastics. But how effective was that? And most of the reports say that they are not effective at all. And now we need to understand why was it not effective? Because there are no alternative materials that can actually give you the same set of properties that plastics give. So I have a couple of examples here. Can we move away from plastic straw and a plastic cup to a glass and silicone metal straw? Can we move from a plastic container to a glass jar, or from bottle to a metal container, or a plastic ice cube tray to a silicone cube trays? Yes, of course we can, but the economics don't match up. And that's the reason why other substitutes of plastic was not all that great. And since we have banned single-use plastics, there are all kinds of alternative materials claiming to be biodegradable. And I'll show you in a while what all we have in the market which claims to be biodegradable, but they are not. And therefore, single-use plastics are again back in the market, but now maybe under the table. The vendor might give you under the table, but not openly. But this is what is happening, and since there is no accountability here, and there are no sustainable substitutes for plastic, we still keep using them. So as I posed a question that should we turn into biodegradable or biocompostable plastics, since the plastics are non-degradable and they remain in the environment for millions of years. So do we find alternatives in biodegradable and biocompostable? Before I get there, we also should know what's the difference between a biodegradable or a biocompostable. So as you can see here, compostable is one of the major part of biodegradable materials, but this needs a special kind of enzymes to break them. and make smaller molecules from it. There is also something called oxo-degradable. It doesn't completely dissolve, but leaves something called microplastic, which is again worrisome. And of course, all the fossil plastic that we just saw never become or can't be degraded, and therefore they keep becoming microplastics. So I have a very beautiful images from PLA, which is polylactic acid, which was under the soil for a couple of months. And this is what it ends with, right? You can still see bits and pieces of plastic, which might take some more time to reduce. But the question is, does it completely reduce into harmless molecules? Is the question. And the answers is no. So therefore, most of these biocompostable plastics, which are not degraded in a special way, often remains in the landfill, very similar to your synthetic plastics, and produce microplastics. Unless an industrial composting setting is available or made available to public, this cannot be solved. So this is a very recent report, maybe yesterday, that New York City considers banning of these detergent pods, and they have a cover of polyvinyl alcohol, PVA, on it. And they found that these detergent pods, when PVA is supposed to be a degradable material, leaves behind tons of microplastic in the drain. And that's the reason why they're planning to ban it. So this is one of the reports which claims that it has found microplastics from PVA. And there are, of course, tons of reports that keep coming every other day saying that your water bottle has millions of microplastics in it. So these news or reports one needs to digest with care, because if this water bottle contains microplastic, and if this water was filtered through a reverse osmosis membrane, which actually removes everything that is sent to it, from where are the microplastics still in the water lines? So is it coming from the water lines, which connects the water filter to the bottle, or it's coming from somewhere else? So these things needs to be digested with care, and also it needs more detailed analysis before you can start believing them. So the solution is, whether should we turn towards biodegradable, yes or no? We will see in the later part of the slides whether we can think of some materials which completely degrades into very simple molecules that don't harm us. So these are some of the regulations in India, and in February 2022, the EPR, which is called Extended Producer's Responsibility, where the amendments were made to this rule. And this is one of the letters that I got from the internet, which says that recycled plastic can be used for packaging, storing, food dispensing. However, it has to strictly follow the guidelines of food safety and standard regulations. So extended producer's responsibility is something which is very, very important, because it keeps a tab on how much plastic you send it to the landfill. And if there is a way that you can consume some of them again for packaging applications, then you don't have to discard them after 1 or 2 uses. So therefore, these regulations are going to be even stricter in future, and we would see an increase or a spurt in the growth of recycling of plastics for various applications. So of course, there are some good news. I just made you sad by showing you many disturbing images, but let me show you some of the applications of plastic recyclate or PCR products. So this is from Shakti Plastics, where they made furnitures out of recycled material. Akshay Kalpa is one of the leading milk suppliers, and their boy tries to collect all the LDP or LLDP packets the next day morning. This is from Manjushri Technopack Limited, where they have recycled material back to the product, which they call it as born again. And this is one of the startup which actually uses MLPs, which comprises of chips and biscuit packets, and they convert them into sunglass frames. There are more good news. So Steer is trying to design an extruder which can actually sanitize all the PCR at the same time and give out materials which can be used for various applications. And their extruder doesn't collect only a single source, but it can accommodate multiple sources of waste. That's very interesting because you can literally throw anything in the extruder and you get shreds which can further be used for different applications in the molding. So this is from mass trans, where outdoor furnitures are made from recycled material, and we have tiles which are again made from PCR olefins. The Castrol bottles that you see are from Manjushri, which contains above 8% of PCR, and the recent studies show that they have been able to dose with 60 to 70% of PCR. This is one company called Voila, which converts all the PCR material into useful products using 3D printing. And as you can see on the slide, that all these products need a very, very strict margin of processing conditions, without which it is very, very difficult to convert them back into useful products. There are more good news here. So these are brooms made out of PET bottles. EcoCari converts all the PET bottles into fibers, and these fibers are then used to make very, very different products. This is one example where PCR HTP is used, and this is the other example where PCR HTP is being converted into gallons of this sort. So yes, there are lots of opportunities there, but how easy or difficult it is to recycle plastic is something that we are going to see in the next part of the talk. So let me give the stage to Sushila. If there are any questions in the chat box.
Thank you, Surjo. This was a very interesting first part of the talk. And you did bring out a very strong call to action, in a sense that the environmental impact of all of this plastic and microplastic and what it is doing to the planet came out very strongly. And we will look forward to the second half where you talk about the solutions.
Right.
But there are a few questions, and the first one is to do with microplastics leaching into the soil. You mentioned about how it ends up in the food chain, and therefore the health impact on us, and whether it's the vegetation or flora and fauna around us, and what is the impact of all of that. There are studies, I believe, that talk about how the microplastics can result in autoimmune diseases and other diseases. So your comments.
Right. So microplastics, of course, is an emerging pollutant, but I would rather say that there are other emerging pollutants which one should be worried about is PFAS or pesticides, antibiotics, which are much smaller than the microplastic. As the name suggests, it's microplastic, which means it can be easily removed. So there are research going on around the globe where they have come up with hydrogels which can actually absorb microplastics from water, or there are membranes that can remove microplastics, and all that microplastics that one has filtered can actually be put into use. But the question here is, why are the microplastics in the soil or in the water at the first place? So if they would have been recycled effectively, we wouldn't have been discussing about microplastics. But there are, as you said, there are tons of reports which keep saying that microplastic in water and in the food chain, that's because of the fishing nets that keep deteriorating over a period of time, because most of the fishing nets are left in the ocean and they don't degrade, but they break down into smaller pieces. Then it enters the food chain and finally it reaches us. So yes, it's a concern, but we probably need to think of solutions that stop them from getting into the food chain or stop them from getting into landfills and the soil or maybe in the water.
Okay, so here's another question asking for details of the organization that calculated the plastic overshoot day. And if do you have some details of the process that was followed?
So this data was taken from the reports. I think it was there in the slide. I'll just go back to that slide. Yeah, so this is from Plastics Europe and CSE India reports. But I also got someone on WhatsApp saying that the CSE reports may not be that accurate, and we need to look for more more reliable sources like Plast India and so on. I think Shapunda, thanks Shapunda for alerting me about that on WhatsApp. So of course, that date is something that has been reported by one of the reports. Plastics Europe and CSE both jointly together have said about this. But of course, every data needs a lot of analysis to see whether it really is. But the message is that solutions need to be found in war footing.
Right. And one more question again to do with the data that you had presented earlier, which is about the FMCG sector and the plastic generation. So the question is, what about the plastic that they claim they've taken back and done something with? Is there data around that?
Right. So the plastic that they have taken back, as you can see here, is very, very small. So this is something I have the data from, again, reports, which says 11% of the plastic is what they have taken back. And those numbers are pretty small given the tons of plastic that they have put out in the market.
Okay. Apparently, Hindustan Unilever has reported a much larger percentage of plastic they've taken back. So you may want to check that out at some point of time.
Right.
And then there are a few questions around how we can prevent diffusion of plastics in water, especially in construction.
I didn't get the question. How do we
prevent the diffusion of plastics into water, leaching of plastic into water, especially in the construction area?
Okay, so again, it goes back to the same question that how effectively are we managing the plastic waste? And the point here is, since they were not managed well, and that's the reason why they are broken into smaller pieces and then they enter either the food chain or let's say the water resources. So we know that the plastics that are being used around the construction area is mostly fossil derived. They're not degradable materials. So therefore, we need to take care of these plastics post-use and try to dispose them off in an efficient manner or try to recycle them in an efficient manner so that they don't go out and plug or the landfills and so on.
Okay. And here's a suggestion saying that we should, the government should put a plastic tax on FMCG companies, which will force them to find other alternatives.
That's true. So more stricter regulations should come in place. And also, especially the FMCG companies which claim that they have taken back most of the plastic that they have already put in, there should be some organizations accountable for this and so on. So therefore, according to me, more stricter regulations would do. Just banning them will not help. Banning did not help, as we have already seen it. So I think stricter regulations will certainly help us to recycle plastic waste that is already generated.
Yeah. And of course, you talked about the importance of consumers' responsibility as well.
That's true. That's true. So every individual needs to dispose the plastic in the right bin. But the problem here is we don't find bins where it should be. And that's the reason why they are littered all around the place, except for airports where you see 3 different bins classified, labeled very neatly. But then what happens after the collection system is something that we don't know, whether they get mixed up, finally ending in the landfill and so on, is something that more stricter regulations only could help sort out this problem.
So maybe, Surjo, now is a good time for you to do the rest of your presentation, because there are a few questions, but I'm sure they will partially at least get addressed with the rest of your presentation.
Sure. Thank you, Sushila. So this is where I left you, that how do we recycle plastics, especially the polyolefins? And I said that there are two major ways of doing it. One is mechanical recycling, and the other one is chemical recycling. And chemical recycling, of course, involves a lot of harmful chemicals. That is again a problem for our environment. And therefore, if one needs to follow this, there are lots of regulations that prevent them from using these harsh chemicals, because one needs to get rid of them at the end. On the other hand, the mechanical recycling is a better and a sustainable alternative. And this is what we have also been trying to do in IISc with help from Manjushri Technopack Limited. Of course, there are other ways of recycling, but let's focus more on the mechanical recycling, because that is one of the easier alternatives and it's more environmentally friendly. And therefore, most of the research that you see today are all centered around mechanical recycling. But as I said, that mechanical recycling, as the name suggests, is not that easy, because there is a lot of science behind collection, sorting, cleaning them, and finally making them pellets. And whether these pellets are suitable to make the same product is a big question. And in most scenarios, one would see that the product that came out after all these cycles have actually much lower properties that doesn't allow them to be used for that particular application. And that's the reason why they're not popular, maybe, or if the cost incurred in all this process makes them more expensive than the virgin polymers or the plastics, then there's a big bottleneck there. So one is economics, where it has to be at par with the virgin plastic, or it should give properties which are much better than the virgin plastic, and therefore they can be used in various applications. On the other hand, if you still remember the term PIR, which is post-industrial recycled material, are less contaminated because they did not leave the premises of the industry, and therefore they can be recycled much more easier than the post-consumer recycle that is from the consumer's end. Now, the question is, how do we improve the properties of PCR so that we can actually put them into good use? And we turn around and looked solutions everywhere, and we found a solution in chemistry. And therefore, the new term called Vitrimer emerges, which consists of adding certain chemicals or agents to the PCR to improve its property, not only mechanical property, but also its physical and chemical properties, so that they can be used back into the same product that it was made from. So as I said that it's not easy. So what happens when we try to recycle? Let's focus only on polyolefins. So this is the virgin polyolefin. This is the regrind, and therefore it has been recycled, let's say, 5 more times. MFI is a melt flow index, which tells us about how easily this material flows under heat. And why is this important? Because most of our polymer processing involves heat and shear. So you masticate them and you try to mold them into various shapes. Now the question is, the virgin plastic flowed well, but why can't the recycled material flow that easily? And the answer is that when you start recycling any plastic for that matter, there's a lot of chain scission that happens during processing, because you are heating them up and at the same time you're shearing them apart. So therefore there are fragments of chains, which then becomes a liquid-like material and it flows very easily. So when some things flow very, very easily, we say that the MFI has gone up, which means higher MFI is a big no-no for various processing, because if it drools, if it flows like water, that's an exaggeration, but for your understanding, if it flows like water, then it's very difficult to work with them. So therefore, MFI control is something that is very important and which is a biggest bottleneck in all recycling materials. And if you see here, the mechanical properties along with MFI also deteriorates. So the first cycle had about 16 MPa of yield stress, which keeps falling with every sequence of recycling. So this is the biggest problem with any plastic recycling, that the product that you get post-consumer recycled material is not same as the virgin material. So how do we tackle with this? We can add additives, but at the same time, we also need to know that post adding additives, whether the regulations allow you to make same product, maybe food, non-food applications, or whether these additives actually do something else, which becomes or which makes it even difficult to recycle in the second and the subsequent cycle. We'll get back to here. We'll get back to this again. Let's take a look at PET, which is again the most used plastic, as you can see everywhere. PET, on the other hand, is also downgraded during recycling or during processing. But this downgrade of PET actually helps it in making fibers. As I said here, that when you heat a plastic and try to shear them, they become liquid-like material. That is exactly what happens to a polyester. When you try to recycle, they become more and more liquid-like. But PET has a very, very significant advantage that when it becomes liquid-like, it can be spun. Whereas in the case of polyolefins, to some extent it can be, but not as greater extent as polyester. So therefore, you have a very nice business case with polyesters. All the used bottles go back to the recycling plants where fibers are drawn from PET bottles. And as you can see, this is one of the genes from the landfill, that the plastic left behind by the genes is all the polyester that is left here, and the cotton is degraded. So therefore, in the case of PET, there is a well-defined business case. From bottle to fiber is called downcycling, and PET bottles are the most segregated ones, and they are often clean if they are sorted and if they are collected well. Whereas in the case of polyolefins, the challenge is more, because since polyolefins are used in FMCG companies, so their production and their waste is huge. And in order to put them back into the circular economy, one needs to do a lot with this effect and try and find out solutions where it can be put to use again with certain alterations. And what this manipulation or alteration can do is the chemistry that we have been also working on. So let me give you, let's step back to see what are these Vitrimers which convert the regular PCR into useful products. So Vitrimers come from covalent adaptable networks, or rather CANs, and they rightly sit at the interface of two broad class of plastics: thermoset, like epoxies, where once you process them, you cannot remold them. And the other side is thermoplastics, which you can keep processing them n number of times, but each time you do, you lose the properties. So can the covalent adaptable networks help in bridging the properties of a thermoset in the thermoplastic? And the answer is yes. And there are various reports which tell us that if you suitably design a molecule that can react with your plastic post its use and form a network that is not permanent like a thermoset, rather the network is a dynamic, then you can keep using that for n number of times before you can put them into circular economy. PET is again a classical example, so I brought this again here. So chain extenders for PET was well known over ages, and people knew that when you process PET, they break into fragments, and these fragmented PET chains can again be joined by various molecules, and epoxy being one of the most used molecule that joins the PET fragments. Now the question is whether we can adopt this in polyolefins using cans. Before we get there, there are two types of cans that you can see on the slide. One is called dissociative can and the other is called associative can. So I'll not confuse you too much. I'll just tell you the difference between the dissociative can and the associative can. As you can see from the pictures here, in the dissociative can, there is a loss of network integrity at some point of time. Whereas in associative can, since these partners quickly try to find its neighboring partners, so there is no loss in the network. So when you have two molecules that can react with each other, right? If you break them, they can quickly try to find the partner and react again. So they form an associative can. Whereas in the case of dissociative can, they try to look for the same partner and therefore there is a loss in integrity. Whether such molecules can be used to give life to polyolefins is something that is very, very interesting. So we focused on associative cans because we know that if you design such a molecule which has dynamic bonds, which means you can break and rejoin them n number of times without losing the network integrity, it gives you a fixed cross-linking density, very similar to epoxies. But the major difference here is epoxy is a permanent crosslink, which means you cannot break them, whereas what we have here is a dynamic crosslink, which you can break them. So all these chemistries trigger at certain point of temperature where they can start exchanging with neighboring partners, and at any given point of time, they are not left alone. So that means that they keep forming network, which we call as topology, and this network topology rearrangement helps them to gain the network at any given point of time during processing or post-processing operations. So therefore, they have the properties of a traditional thermoset, but at the same time, they offer you to recycle them n number of times. So you might ask me, what is the difference between a reactive extrusion and cans? Yes, there is a whole lot of difference. In the case of reactive extrusion, which many of you might follow, that you have malleated polypropylene. As you can see that there are maleic anhydride groups. You bring in molecules that can permanently form covalent bonds, which means if I bring an amine closer to this anhydride at higher temperatures, they quickly bond. But when they bond, this particular chemical bond is permanent bond, and you can only break them at higher temperature, but you cannot cut them and rejoin them. So this is the difference between reactive extrusion and dynamic bonds. In the case of dynamic bonds, you can break them, but they again join them, which gives us a sense that they can be self-healed, they can have a shape memory effect, and so on, which also means that the Vitrimers can be regrind and can be again made into a same product without loss in the property. So in the case of reactive extrusion, you might be able to get upcycled properties, but that's only once. When you try to recycle them, you will again face the problems. And there are studies which shows that how strain hardening decreases with increased shear rates or strain rates in the case of reactive extrusion, where the bonds are permanent. Whereas if you introduce dynamic bonds, then you should be able to make very useful products post its useful life, because you have a topology freezing temperature which allows it to recycle at a particular temperature. So which means that you have, let's say you have an original shape, you can give it a temporary shape, it can come back to its permanent shape, and you can keep doing this because you have bonds that allow you to do so. So therefore, dynamic exchangeable bonds are quite interesting and have been known in chemistry for ages, but it has picked up in recycling olefins, or rather other polymers, very recently. And there are tons of reports these days which tells about how polymers can be recycled using cans, which are covalent adaptable network. So before I get on to show results from my lab, I thought let's show you some of the results from the literature. So this is one of the study from polyolefin Vitrimers, which has been published in this particular journal, Journal of Materials Chemistry A. And you can see that the starting material is polypropylene, which could be PCR polyolefin as well. You have malic anhydride, and with little temperature and DCP, you can actually graft the malic anhydride onto the polyolefin chain. This step is very important in polyolefins because polyolefins lack in any chemical bonds that can actually bond with any other chemicals. So therefore, it becomes very, very tough to graft anything on polyolefin because there are no functional groups that are available. So once you start with this material, then there are n number of materials that can help you to form dynamic bonds. And this is one example where epoxy was used to react with anhydride, which is called epoxy anhydride curing, and you have a dynamic bond. And this dynamic bond helps to improve the properties of the recycled material. This is polypropylene, which is neat, and the Vitrimers have much higher tensile properties. But the question is, whether do they have same MFI as that of PP neat is a question. It's not reported in this study, but I'm sure getting to the same MFI requires a lot more than what you're seeing on the slide. So just to bring to your notice what post-consumer recycled olefins means are all these products that you see. The bottle cap is made out of polyolefin, the bottle is made out of PET, and the trays are made out of olefins and so on. So basically you shred them, clean them, sort them based on color, and then you come up with PCR, and you can do this exercise to improve the properties of the same material. If you are able to do so, we call it that you have upcycled. And upcycled PCR again has a lot of potential uses in various applications. Whether it can go back to make a cap is something that is defined by food regulations. But in general, they can be used for any applications for non-food applications. Let me show you something from polyethylene. This is high density polyethylene. Again, a simple chemistry gives opportunities to recycle them at least 5 more times before you can discard them or before you can see them that the properties deteriorate and so on. So this is all the post-consumer HDP that we see around. So basically PCR HDP means shreds of all these products. And I have witnessed how they come, in tons, and they have shredded, and the robotic arm sorts them based on the color. And all the white ones have more applications, so therefore they are sorted, and then they are recycled in the same way that the virgin plastics have been processed. So now let me move on to our approach. We have seen a lot of literature on polyolefins where they have been trying to upcycle polyolefins, but MFI is still a concern. Whether they flow in the same way, the way the virgin polymer did, is a major question. So what we did here in IISc is we chose an oil, which is a non-edible oil. So therefore we don't meddle up with the food security. So we took this oil and we made a lot of derivatives of this oil, for example, epoxidized, or you can introduce some malleated groups and so on. So this is the post-consumer recycled polyolefins, which we sourced. They come in the form of chips. So you take this, you mix this oil, and you add certain agents in an extruder, and you form a compound. So this compound, which is called PCR olefin with certain ingredients, is little special from what you saw from the last 2 slides. This oil helps in homocross linking, which means that the 2 chains of polyolefins is not only connected with this molecule, but they also form some homocross linking within them. So this helps us to control the MFI, and therefore our PCR PP, we were able to control the MFI, whereas in the literature, most of them reported the MFI shoots up. Not only that, we were also able to upcycle this material because of the dynamic bonds that you see here, so this is the PCR PP as received, and you can see that in one of the cases, we were able to upcycle both the strength as well as the modulus and also the elongation and break. So this particular oil doesn't degrade during the processing of polyolefins. That is the beauty of it. And this oil actually helps in improving a lot of network connectivity within olefins. And that's the reason why we see a lot of upcycling. So since this talk is all about emerging solutions for recycling, so we put our material to test. And we did this exercise for 5 times where we extruded, we molded, we cut them into pieces, we put them in the extruder, and we repeated this cycle for 5 times. If you do this exercise for the PCR olefin straight away from the market, you would see that the tensile strength drops significantly with each recycling sequence. The MFI shoots up with every recycling sequence. Whereas when we use our own PCR containing this special oil, we see that even after the 5th cycle of recycling, there is highest recovery, which means we were able to restrict this drop in mechanical properties and also restrict the increase in MFI. And that is because the homo-cross linking that was introduced together with the covalent adaptable network helped us to recycle the material for at least 5 times to show that the properties don't even change, and therefore they can be put to multiple uses. So now let me show you where these materials are going. So this is our PCR olefins, which is modified with this oil. They have a controlled MFI. They are upcycled. And we saw that there is no compromise post recycling. So in our bid to emerge or give sustainable solutions, we tied up with Voila. And what they did is they tried printing this PCR into various useful products that you can see. And in order to print it, they need a strict MFI band of 5 to 8, which the PCR that we received from the market had about 30, which means they flow very easily. But in order to put them or in order to print them, you need material that has a count between 5 and 8, which means they should have the right viscosity that you can make them print them into products. So since our PCR, we were able to control the MFI, and at the same time, we were able to improve the structural properties, we were able to print them into various products. And these products very soon will hit the market, and they are sleek and elegant, and they can compete anytime with the products that are out in the market. So in our race for finding sustainable solutions, this is one more product that is doing rounds in Amazon, where the filter here is coated with greener polymers extracted from green tea. And we could see that we were able to give some sustainable solutions for filter media applications. And this was during COVID, where we were able to find, let me see if I can run the video. So we were able to produce fibers from biomaterials, and these bioplastics can then be coated onto a HEPA filter. And when you actually coat them, they form nanofibers, and these nanofibers nicely adhere onto the filter media that you see here on the slide. And all the germs or the microbes that you see in the air gets trapped into the microfiber. This is how it is being sprayed. So this is a biopolymer, and it has active ingredients which interacts with the microbes and quickly deactivates them. And that is how you can produce clean filters. So now we are trying to make the HEPA filter out of a bioplastic so that at the end of its useful life, when these filters hit the landfill, it should degrade on its own, or it should offer us composting facility where you can compost them under industrial settings. So we are also working with a company called Y-Weight. So they produce containers for packaging cosmetics. And again, we took the examples, or we borrowed the chemistry from Vitrimers. We made a polyvinyl alcohol which containing molecules that allows it to recycle n number of times and also upcycle it. So we are now working closely with them to make these containers. And the beauty is at the end of its use, you just have to put it in hot water and this all dissolves. So in our bid for sustainable solutions, we are trying every day to find out solutions that can help reducing the burden on the landfill and whether the plastics can be dissolved or can be composted in the right way, or at least can be recycled the way I showed you on the slide. So this is my last slide, and I will leave you with this video. This is a viral video which is making rounds on the internet. How this beast did not like the water bottle at the wrong place. It picked it up and it tries to dispose it off from the water body. So this is from the Tadoba National Park. So the question here is, it's just a behavioral change that can improve and encourage waste segregation in India. So if they can, why can't we? Thank you.
Thank you, Surjo. That was a very interesting and the last bit very sobering as well. So
Thank
we
you.
have a bunch of questions. Let me start with a few around definition. So here is someone who wants to know why, and this is about the definition of downcycling and upcycling. And here he says, what is the conversion of bottle into, why is the conversion of bottle into fiber called downcycling when the final product, which is either fiber or textile, remains in use for a long time, as against plastic products which also have a shorter lifestyle, span. And a second question is, what distinguishes upcycling polymer from secondary recycling polymer? Are they being used interchangeably in the same context?
So the definition of downcycling is when you process a polymer once and you see that your mechanical properties go down significantly. That's called downcycling. And that is exactly what happens in the fibers, where you start with polyester, which has excellent mechanical properties. But post processing it, you see that the mechanical properties go down, but that's right enough to spun them into fibers. Now one may ask that why can't we just spun the virgin PET? Yes, you can. With certain modifications, you can always spun or spin PET. But here the question is, after you have processed it once, since the properties have gone down, and that is rightly needed to spun fibers, so we call it as downcycling. Of course, the application doesn't mean that it is downcycled, but it is the properties which got downcycled.
Okay. Someone wants to know if the oil that you used in your lab, is it synthesized in the lab or has it been procured from the market? And
So this is a natural oil abundantly found, but it is a non-edible oil. And that was the reason why did we choose it, because India is the largest producer of this particular oil. And therefore we thought, why not use it for a purpose which can help recycle polyolefins. And it's an FDA approved oil. So therefore, let's say we make some Lego toys out of this particular polymer and the kids, try to put it in their mouth. So therefore, the ingredients that goes in is very, very important.
Right. A couple of questions around very specific around, is it possible to use functionalized SBR as a chain extender? And if yes, can it act as a HIPS? So that's the...
As a HIPS, HIPS?
Yes.
Right. So functionalized SBR, of course, is a wonderful material and can be used. So all that you need to create a covalent adaptable network are the right functional groups. For example, as I showed, epoxy and acid can cure. There are disulfide, there is click chemistry, and a whole lot of chemistry that is out there, which helps us to install covalent adaptable networks in the olefins. So yes, functionalized SBR can always be used to upcycle HIPs or polystyrene for that matter. And if the bonds are dynamic in nature, you will see some upcycling.
Then do you have any information on the time, temperature, superposition, master graph?
Not today, but there are literature which gives time temperature superposition of Vitrimers, because once the covalent adaptable networks are installed in a particular polymer, let's say PCR olefins, they show a telltale signature of rubbery region, especially in certain characterization, which tells us that these materials are just not like the virgin material which flows. So it has sufficient strength even in the melt, and that strength is coming from the dynamic network that we have created during processing. So therefore, there is data available, but not today with me, but of course in the literature.
So the next set of questions is around recycling itself. One of them is the complexity of recovery. So if you took something like e-waste, which also has a lot of plastic in it, how complex is it? Is it doable, not doable? And similarly, when you have multi-layer materials like Tetra Paks and so on, how does it work?
So e-waste is again, a big concern, and e-waste mostly contains plastics, and of all the plastics, ABS is one which is dominating there. So we have been working with ABS for a while now, and we came up with solution where one of the derivatives of this oil actually helped in upcycling the ABS. And therefore we were discussing with companies which would be interested in upcycling the e-waste ABS that comes from the e-waste. So therefore, there's a lot of opportunities in recycling of plastics using this particular chemistry, which not only helps them to upcycle, but it also controls their rheological properties. And these rheological properties become very, very important for polymer processing.
Again, which plastics are recyclable, and are there specific rules around recycling of different kinds of plastics?
So practically all thermoplastics that we see around, except for the thermosets, are all recyclable. But the fact here is when you try to recycle them, you don't see the same set of properties that it showed earlier. And that's the reason why they are not being recycled effectively. But now if there are solutions which can help, and of course, borrow the chemistry from covalent adaptable network, install in them, I'm sure they all must be able to recycle.
Now, recovery requires a lot of energy and other resources. So at what point of time would you say that it is not worth the effort and cost of recycling or recovery?
So right now, the recycled plastic that is available in the market is priced very, very similar to the virgin plastic.
Okay.
And in some cases, it might be slightly higher. So now some say that it should be higher, and government regulation should strictly say extended producers responsibility, that you need to buy the recycled material and put it back into the circular economy. And the other school of thought says that if the cost is slightly lower than the virgin plastic, then it makes much easier for the vendors to use them and put them into useful life. So yes, regulations have to be much stricter here. And since recycling is the only way forward, and there is no other alternative that I see right now, because converting all of them into biopolymer or bioplastic is not feasible at all. Because as I said in my slide, that if it is a biocompostable polymer, it behaves very similar to your fossil polymers. if you do not compost it in a right way. And in India, we do not have industrial composting units everywhere. So therefore, if you think that you are using a bioplastic cup and just threw it in the landfill, assuming that that would disappear, it would in fact become microplastic, but not disappear. So therefore, it's very, very important that we need to have a balance and slowly phase out wherever we can with plastics that can degrade on its own. And where we can't use them, we should strictly recycle them, or rather aggressively recycle them.
And is chemical recycling economically viable?
Answer is no, but the products that come out from chemical recycling are very, very interesting because they can not only address the recycling, but they also give out energy, an alternate means of energy. So currently the economics don't work out, but yes, chemical recycling, if it is, efficiently followed, it can do wonders.
Can you throw some light on what challenges the recycling industry faces in managing plastic waste?
So since we are working with a couple of companies now, we find that sourcing them is a major issue. Sourcing them, which is called single-use recycled material, which means they all come from the same brand or same product. Sourcing them becomes very, very challenging. And when we have sourced it from the market, we saw that they throw up all kinds of properties. So they vary a lot from source to source. So yes, recycling is a challenge at the moment because of all these bottlenecks. One is sourcing the material. Second is how clean are they? And if the regulation says that you can use it for food applications, whether we will be able to comply with the regulations and so on. So I think there should be more focus on, if there is encouragement from government side, there would be more focus on effectively sorting and collecting them. And you should be able to, get single source PCR materials, which actually gives much better properties from a mixed source.
Okay, then here's another question on the process itself. Is it possible to reverse the bond at room temperature, especially for trans-esterification reactions?
Not at room temperature, but slightly higher temperature, maybe around 60 to 80 is activation energy where you can reverse the bonds. Trans-esterification, imine, disulfide, and there are a whole lot of bonds that gets activated at certain temperatures. So room temperature, you can cleave them by enzymatic ways, but not by temperature.
Is converting polymer waste into fuel more economically viable than upcycling? And what factors contribute to this comparison?
So currently the answer is no, because the infrastructure that is required to convert plastic waste into fuel is pretty expensive and it needs huge infrastructure. And I think if you see the statistics in my slide, the chemical recycling is a very, very small number. I would say that is at the infant stage at this moment. But however, if effective solutions emerge, I think chemical recycling and converting plastic waste into fuel could be a very, very interesting subject.
You talked about the fact that there is, while it is important to regulate and so on, we can't really regulate ourselves completely out of this mess. And therefore, there is a responsibility on the consumer, that is all of us. What is that and what can we do about it?
That is very much true. And there are two taglines which was there on my second or third slide, that don't ban me, but manage me better and retire me at the right time. So we tend to use the single-use plastic multiple times and then we complain about microplastics. But why can't we throw the bottle after single use so that it can be recycled in a much more efficiently? So right now, the recycling business whole lot depends on sorting, collection, contamination, and so on. But all this could be minimized if they are effectively collected at the first place. So as a responsible citizen, I feel that everybody should contribute And also make sure that you might segregate them at your home, but it's not being done at a larger scale. So that is something that as a citizen you can't do, but regulations can do. But as a citizen, we should all, retire the plastics at the right time so that they can be given a new life.
Why should we prioritize upcycling over fuel production from polymer waste, especially considering that 90% of plastics are derived from fossil fuel?
Yes, so one of the strategies is converting plastic waste into fuel. But as I said, that since it's infrastructure heavy, it becomes a lot more difficult to set up plants which can convert this. In future, we might see this happening more because stricter regulations will be in place. But at this point of time, upcycling plastic waste is a much more effective solution given the amounts of plastic on our landfill. So we first need to reduce them. We need to collect back all the plastic that is littered all over the place. And mechanical recycling has a much lower turnaround time. And that's the reason why it's a most effective way.
Right. Okay, I think we are done with the questions.
Okay.
What remains is a remark from somebody in the audience who says this was an excellent talk.
Thank you.
So
thanks a lot.
with that, thank you so much, and I'll hand you over to Abha.
Thank you, Sushila.
Thank you. I'm sorry. Thank you so much for thank you so much, Dr. Bose, for this insightful and very deep discussion on a very urgent topic, which is, I think, the requirement for not only its country based, but the globally we need to be concerned and the address the issues and the solution which you have proposed. Probably maybe not very far, but near future, we should be able to implement and we can make these processes very cost effective. That's what we look for. But this talk was really very informative. I think anybody, I guess, is able to know that or able to understand that, look, this is not something which is right, and that this plastic waste is not something we really have to go somewhere deep down to figure it out, but wherever we go for just pleasure, and we see that the chunk of plastic just lying down, and it, irrespective of it is the ground, it's dry waste, or it's in water, everywhere. So certainly it is affecting everybody's life every second. And this, at this moment, this talk actually weights a lot. And we got to know that this plastic overshoot day. So we are actually overshooting the management capacity. And as you rightly mentioned, that this 28th July 2023 is marked as very important day. So it's alarming, and we got to learn that a lot of technical details, which is like having the post-industrial processes and also the post-consumer recycling. And as you mentioned that this contains a lot of contamination when we are consuming and trying to the recycling it. So certainly something which is one needs to take care. And we learned about this multi-layer of the challenges associated with recycling are the multi-layer incorporation of polymers, which industries probably have to come in and really. So what I find very interesting is your collaboration with industries directly to solve the issues directly with them, because these are the companies, as you mentioned in statistical data, that look, there is a very less component you are using for the recyclable plastic, but there is much more you have to do. And this is really very interesting. And so we learned about the chemical processes. You mentioned that probably it is not too tedious. It's not really, one cannot afford, but it's a matter of time when I think we'll have just on spot like recycling processes, and people should not really maybe look for these bins, but the probably they can just throw in those recycling bin, and within fraction of second we are just able to reach out to a new product, and that's what we look for. And very interesting statistics what you have produced, what you have shown in this presentation, like when Asia is taking a burden of 50% of the total plastic waste, and India comes as a 12.3% of taking it. So we don't want to really have a much more in this number. So we really look for this is much more of the research component, and much more of the probably there is a need for, as you mentioned, that we should be having these the rules, regulations in place, so that one takes the responsibility and first waste can be reduced, and the classical ways of recycling, which you mentioned that these are not really viable solutions, which we have been using. And this really requires the novel methods, which you mentioned, that converting the molecules into a new usable molecules. And yeah, so this is really very interesting talk. And I'm sure those who have missed this talk today, they will be able to access this talk through our YouTube streaming, and this recording will be available to everyone. And I would like to thank Dr. Sushila, so putting a lot of interesting questions to bring in the discussion, and the posing the challenges in a very, very nicer way. So thank you, Sushila.
Thank you, Abha. Thanks a lot.
So much. Thank you.
Thank you.
Bye-bye.
Thank you
Bye-bye.
very much.
Thank you.
Bye.
Bye.